I think it's enough to, for the sake of this course, that there are a few examples that you've seen, a few classic ones. You'll do some coding of it, and that should give you some fundamentals in divide and conquer. Sort of the last topic for the course that I want to do is shortest path algorithms. And then after that, I'll probably open it up for questions and maybe do a lecture on like P versus NP. So we've already seen one shortest path algorithm. We've seen BFS. And so what BFS says is like given an unweighted graph, the single source shortest paths problem, and this is called SSSP, that is single source shortest path. So you have one source and you want shortest paths to everything. The single source shortest path problem can be solved in essentially, linear time, right? O of m plus n time, number of edges plus vertices, right? So this is the fundamental thing that we've seen. And so the question, the whole topic of shortest path algorithms is what happens when it has weights, right? And then BFS won't work anymore. Yeah?
Sometimes graph frameworks have a different algorithm or different implementations for BFS and single source shortest path. Why?
Because it's weighted, probably, right? Or even the unweighted case? Yeah, usually it's BFS works when it's unweighted. So it might be a question of weights. And then, as we discussed, if you only care about one source and one destination, then like the first assignment, you can do by BFS or you can do other kinds of heuristics to get it. But typically, I would think it's because of weights. Okay. So, and the question is, what happens when there are weights? And I probably don't have to tell you that for many applications, especially routing on road networks, weights matter. And so I shouldn't say most, but many applications of shortest paths really, you care about weighted networks. And even in the case of weighted networks, there are two cases. You can have negative weights or, just non-negative weights. So when you have negative weights, the problem becomes a little tricky because, for example, suppose I have this graph, so I have S going to T, maybe this weight is 4, this is minus 5, and this is 0, and the weight of this is 3. Okay, these are the weights. What is the shortest path distance from S to T? Okay, so you said 2. Because you could go up here, you could come down there, and you could go. Okay. But I claim that I could even do better than that. Yeah?
You just go around the times the loop.
You could just go around the loop. You keep going around the loop. So this cycle here, if you go back, start from S and go back to S, you get minus 1. So you can just keep doing that as many times as you want, and then go to T. So it looks like I'm cheating. And why am I cheating? Because I'm using the same vertex again and again. But there's nothing in the shortest path definition that says that you cannot use the same vertex again. Yeah? Unless you enforce that.
Isn't S being at a distance of -1 from S kind of contradictory?
Okay, so you say that if you have a situation like this, then the distance of S to itself is itself not defined properly. Right? So what happens is if there are negative cycles, then shortest path distances are undefined. Yeah?
Is a negative cycle just repeating or referring to any sort of cycle where you can just like perpetually decrease?
Yeah, so negative weight cycle just means that you look at a cycle and the total weight on the cycle is negative. It's as simple as that, right? So this cycle over here, that cycle has weight -1, and because it has a weight of -1, you cannot define shortest path distances. Okay? So you have almost like three situations. You have a situation where there's a negative cycle, so shortest paths are not defined. You could have negative weights, but not have negative weight cycles. So for example, if this instead of -4 was -3, well then it's okay. Then you won't have a problem. You actually can define shortest path distances. And of course, if you have non-negative weights, then of course there's no problem. Now you might enforce, you'd say, no, I want paths where I'm not allowed to repeat a vertex. Right? You could say, in this case, you could enforce paths without repetition. Did I? No. Okay. Repetition. It turns out that if you enforce things without repetition, then it's NP hard. So it's actually not possible to. We don't know if there are any efficient algorithms. So let's sort of ignore this case. Let's assume that when you're looking at shortest path distances, you could have paths that repeat themselves. When you have negative weight, when you don't have negative weight cycles, there's no benefit in repeating a vertex. That's the whole point. Okay, so you have what happens when there are negative weights, non-negative weights, and we'll assume that there are no negative cycles. So in this, actually, there's an interesting question, which is, suppose there's a negative cycle, can you find it? Just to see if shortest paths can be defined. So it's almost like there are like many layers of problems. The first problem is, can you find a negative cycle? The second is, if there is no negative cycle or negative weights, can you find shortest paths? And finally, if there are non-negative weights, can you do shortest paths any better? Okay? So typically what you've seen is all the non-negative weight case. And what you're probably aware is you've seen BFS before, you've probably seen Dijkstra. Right? And Dijkstra works when it's non-negative weights. When the weights are negative, Dijkstra fails. Okay? So instead of going over like algorithms separately, I want to talk about this in what's called a slightly more general setting. So any questions about this? It's clear? Okay. All right. So let's talk about a notion called a distance label. So it turns out a lot of shortest path algorithms can be defined in terms of what's called a distance label. So what a distance label is, so now that we've seen BFS and DFS, think about a distance label as some array that I'm going to call an estimate. So the source, S is fixed. Okay. And I'll say dist of V is equal to the shortest path distance to V from S. So the graph may be directed, it may be undirected, weighted, anything. This is a very general definition. Your aim is to compute these. Right? Your aim is to compute these and also find the actual paths that obtain the shortest path distance. What I'm going to maintain is something called a distance label. So this is going to be an array of estimates to the shortest paths. So I'm going to maintain this, and I'm going to maintain a predecessor array just like BFS. And what I'm going to do is I'm going to give you the invariant, the property that always holds. Okay, so does this make sense? I'm going to maintain these two arrays, or rather this array is called a distance label if it satisfies some properties. I'll tell you what the properties are. So the main property is that est v is greater than dist v, sort of at all times. So one way to think about this is your algorithm is maintaining this estimate, and the estimate is always an upper bound. Okay? And then secondly, v, predecessor v, predecessor, predecessor v, so on and so forth will go to S, is a path, like in reverse, of weight exactly estimate of v. Okay, what this means is that if I follow the predecessors, then the excuse me, the weight of that path is exactly my estimate. Okay? And usually this is what distance labels are. So this should seem familiar. This is a lot like what BFS is doing. This is a lot like the end state of BFS. But if you look at the intermediate state, I want to talk about what happens with this estimate. Okay? Is this clear? Okay? So you can actually, if you sort of strip away a lot of the details, you look at any shortest path algorithm out there, what they're doing is typically maintaining these. Like if you've heard of Dijkstra with A star or various heuristics of Dijkstra, it's basically maintaining some estimate. And what does it mean for the estimate to converge? If it finally reaches dist v for all v, then it's done. The algorithm is done. Yeah?
How do we initialize our estimate?
Yeah, okay, so good question. How would you initialize the estimate? What should you initialize the estimate? Yeah? Infinity, right? You set everything to infinity except for 1, which is the dist of S to itself is 0. Which, if you think about it, is a lot like the visited array, right? The visited array sets visited of S to be true and everything else to be false. Right? And if you think about it, as soon as in BFS, when visited becomes true, at that point actually the estimate is the true distance. And this is not necessarily going to be true for all algorithms. Okay. So once you have this framework, you can actually view BFS, Dijkstra, Bellman-Ford, all these algorithms as simply doing updates to this in some order. And the whole game is to choose the order to do these estimates, to update these estimates. Okay, does this make sense? Okay, so now let me ask you a question. Suppose you have these estimates. Can you think of an operation that will improve your estimate? Like, how would you improve these estimates? So I give you a bunch of estimates already. Yeah?
Start with the shortest, the
Smallest weights and do what? How would you update the estimate? How does BFS update its estimate? Yeah? Find the minimum and do what? Like so I give you so let's just say what I have right now is I have these arrays. Right? And I tell you actually these are not the right answers. What should you do like there's a simple operation that you can imagine. If you think about what BFS does, yeah?
I guess if it discovers like one of the edges on the path.
Okay.
BFS, it knows part of it, so then it can update it.
How exactly? Right. So somehow you look at your neighbors. Why would you choose to update your estimate based on your neighbor's estimate? Yeah?
It's a lower bound, like the value from the node to the neighbor is less than the current value of the neighbor. Plus the weight, exactly, right? So what you say is, look, so suppose you have some estimate of V. So you know that there is some path from S to V, sorry, this is V, and this weight is exactly the estimate of V. You know that there is some path that you have. Now suppose you have a neighbor U. You know that there is a path from S to U of length estimate of U.
So if estimate of u plus the weight of uv, so this is what I mean by weight, is strictly smaller than estimate of v, then I've discovered a shorter path. Right? Yes?
While I was answering that, I was wondering, how do you know if infinity minus 3 is less than the other infinity? Because they're both initialized at the same.
So yeah, if both of these are infinity, then there's no way you can do the update. So infinity plus something is also infinity. So what this means is if you have two things which have an infinite distance, then there's no update you can do on them. But if one of them is infinite and the other is not, then you can do an update. And that's exactly what BFS does. If you think about what BFS is doing, when visited is false, its estimate is infinity. And then it has an edge to something which visited is true, then it can do the update. So you can actually revisit BFS in terms of distance labels, which is like a different presentation. It's almost identical, but instead of visited, you'll have distance labels. Okay, so if this is true, if this happens, then what should you do? How would you do the updates? Yeah? So you set this, you reset this to be estimate of u plus the weight of uv, and then there's another property you need to maintain. Yeah? Set the predecessor of what to what? Predecessor of v is going to be u. Right? So this operation which you've discovered is also referred to as relaxation. So it means that relax of uv, I can write this as a function. All it does is just does this. So it takes uv and it checks if there is a shorter path to v via u, via that edge uv. Right? And so how long does this take to run? This operation, if I give you u and v. Yeah? It's O of 1, exactly, right? It's an O of 1 operation. And so the nice thing about this operation is that one way to think of it, it's always a safe operation. Like you're never going to make a mistake. What you're going to do is always maintain these properties at all times. Okay? So the nice thing about doing any sequence of relaxed operations that converges is even if you stop in between, you will always have these properties. And if you've ever seen Dijkstra with A star, that's basically what it does. It's doing a bunch of these operations and at some point decides to stop and say, okay, I don't want to spend more time doing this. And so it always ends up with some estimate, which is always an upper bound and it always has a path of that estimate. It's like the algorithm says, I know that there is a path of length at most that, and here's a certificate that this is the shortest path distance is no more than whatever it provides. Does that make sense? So in the next, or in this lecture and maybe some of the next, I want to view any shortest path algorithm as simply a sequence of relaxed operations. And the whole game is to find out what is the best sequence to perform this in. Okay? All right. Any questions? How many of you have seen this before? Okay, so many of you have already seen this before, so I guess it's not news. Okay. So you have the relax operation. So an SSSP algorithm is a sequence of relax operations which keep updating the distance labels. Okay, good. So the first algorithm that we're going to look at in this context, which is this, yes?
Oh, sorry, I think I missed it. What is SSS?
Single source shortest paths. That just means that I fix one source and I want shortest paths from that source to all vertices. The reason why is there's also something we'll see called APSP, which is all pair shortest paths, which is like I give you a graph and find the shortest path between all pairs, which you could imagine by just doing many SSSPs, but there are faster ways of doing it. Okay? All right. Okay. So let's start with the Bellman-Ford algorithm, which once you set it up is a surprisingly simple algorithm. Okay, and Bellman-Ford can find, it can do a lot, but let's first discuss the Bellman-Ford algorithm. How many of you remember the Bellman-Ford algorithm? Some of you, sort of, kind of? Okay, good. So it's worth going over. So remember, we discussed that the relax operation is like a safe operation to do, meaning that you will never make mistakes. By mistakes, I mean you'll never violate this property at the top. Okay? All right, so here's what the Bellman-Ford algorithm says. Suppose I have some SV. And suppose this actually is the true shortest path. Suppose this was the true shortest path. I mean, I don't know what it is, but suppose there's something that exists. Again, assume there are no negative weight cycles. Okay? Okay, so I'm going to call this vertex U1, U2, U3, U4 up to UK minus 1, and V is just UK. Now, these are the... Now, consider the following sequence of relax operations. Actually, I'll move on to another page. Okay, so is clear? Okay, so let me do the following, and let me refer to S as U0. I'm just going to do relax U0, U1. Then I do relax U1, U2, relax U2, U3, so on and so forth, until I do relax UK minus 1, UK. So I did this, suppose I did it in this order. So I relaxed on the first edge, then the second, then the third, so on and so forth. At the end of this process, at the end, what is the value of S to V? This question makes sense? So this is the actual, suppose this was the true shortest path. And I just for simple, imagine I laid it out in front of the algorithm and said, here's the true shortest path. And what the algorithm decides to do is just to do relax on the first edge, then the second, then the third, so on and so forth. Ignore everything else. What happens at the end? What is the guarantee that you have, yeah? S to V will become dis to V. It will have converged to the right value. Why? Because of the invariant, but why is it going to be exactly equal? This is the shortest path. So what's going to happen is that in the first, you're going to get the distance to U1 correctly. Then you get the distance to U2 correctly. Right? Because if this is a true shortest path, every prefix also is a true shortest path. Right? Because there's obviously no shorter way of going from S to anything in the middle. So what this means is that at the end, not only did you get the value of S to V correct, you got all the estimates in between correct. So somehow if Bellman-Ford could actually follow the sequence of shortest paths, it would get it correct. Of course, you don't know what that sequence is, which is the whole problem. But what is the value of S to V? Actually, S to V is going to be dis to V. Actually, moreover, it's going to be for all I less than K, S of Ui is going to be the true shortest path. What this means is if one performs a sequence of relax operations exactly in the order of the shortest path, then est becomes equal to dist. It will converge. Yeah? And this is going to be true for any shortest path, like not just, whatever. So you take any shortest path, and if you can perform the relax operations in that order, you're guaranteed to work. Now you're going to say, but how? That's the whole point. How do you actually find it out? But now I'm going to say something else. Suppose you did this, and in between, you did more relax operations. So let's just say you did these, but you did more relax operations in between. So you did relax on the first edge, and then you did a bunch of other relax operations. Then you did relax on this edge, then a bunch of other operations. What's going to happen now? Yeah? Yeah? The same thing, right? Because relax is a safe operation. It doesn't change the invariant. Right? We just argued that the nice thing about the relaxed operation is that this invariant is always true. So this never changes. Which means that by doing extra relaxed operations on top of the shortest path, we still get that the estimate is going to be equal to the distance. Is that clear? Yes? Yes, because, this is the shortest path. And because we know that relaxed operations never make an error. They never change the invariant. Once something has reached the shortest path value, it's not going to decrease below that. Right? It's not going to actually update that at all now, because there is no way of that being shorter. And we said that what happens is that for all I less than k, the estimate is equal to the distance. Right? So essentially what happens is, in order, the shortest path distances get correct on each of those. But after being correct on, say, U3, if it does a bunch more relax operations, it's not going to change that fact. That fact is going to remain true. Okay, so far so good. Yes?
I guess I'm not really, I'm still a little bit unclear on what intuitively relax does. You're setting the estimate to the estimate plus the weight.
So no, if it's lower. It's just saying that if there is a shorter way through one of your neighbors, update. Right? What this is saying is simply that if the estimate of u plus the weight is smaller, strictly smaller, then do an update. If not, you don't do anything. So in many cases, the relax operation on an edge will not do anything. It's just going to say, okay, I already found a short path, and there's nothing to be done. Yeah? At this point, you should be able to derive the Bellman-Ford algorithm. How are you going to do a relax operation in this sequence without actually knowing what the sequence is? Yeah?
Is it directed or
Doesn't matter. Pick your poison.
you just do relax on every?
Okay, all right. Do relax on every edge. But you might not do it in this order, right? Yeah? Okay, go ahead, yeah?
Use a data structure that
No. It's not that fancy. The answer is much simpler. Right. So if you, yeah?
So you can just talk to all the neighbors from source, and then we just bring up on similar to BFS.
The problem is that when you're talking BFS, you're thinking of a queue. What is the ordering in the queue? In BFS, all of your neighbors, you just put them in the queue. But technically, depending on their weights, you might have to order. If the weights are negative, well, then it's going to be much harder. What you're talking about is almost like Dijkstra. I'm saying that forget data structure. There's a much simpler way of thinking about this, where I just want to do relax on all of these edges. Yeah?
You could just run relax
Through all edges. Just do it over and over again. Run the relax operation on all edges. You're obviously going to do this. Then just do it again for all edges. You'll obviously do that. And then just do it again and do it again. And you know the shortest path length, I mean, they're not going to be more than n edges. Right? Technically, it's just n minus 1 edges. So that's the Bellman-Ford algorithm. That's it. You just do the relax operation on all edges n minus 1 times. Yeah?
That was my question. I was going to say, so instead of like doing a quote-unquote like graph traversal, you just relax every edge.
You just do it on every edge. It doesn't even matter what order you do it on. It's like you just run through the whole list of edges, do relax, then go back, do it again, go back, do it again. Yeah?
Doesn't necessarily give all the exact correct distances, does it? After the graph runs, it just gives an upper bound.
But if you did it n minus 1 times, like if you did this iteration n minus 1 times, then you've obviously done all of these relax operations in that order, plus some others. But the plus others don't affect anything. It's pretty clever, right, if you think about it. So, yeah.
So what this sounds like to me is it just gives them the minimum neighbor of every edge, and then it just subtracts the extra edges. But what if there was a node, what if there was an edge between U1 and U3? Would it completely
So suppose there was something like this.
Yeah, so would
These are weighted, by the way.
okay.
So that must mean the weight of this edge is much more than the weight of this path. Right? So it's just not going to do anything. If actually this edge had a smaller weight than this path, then this is not the shortest path anymore.
So you say you run whatever, you do relax on every edge n minus 1 times. Is n here the number of vertices?
Yeah, it is the number of vertices, right? Because that's the length of the path. I'll write this down in a moment, yeah. But
Order of vertices times
eh,
number of vertices times number of
edges, yeah, exactly. Number of vertices times number of edges. So it is inexpensive. It's quadratic time. But the bound has stood for 40 years or 60 until last year someone improved it. But it's still it's such a simple algorithm. Right? It's remarkably simple and it gives all shortest paths with negative weights. There's no data structure, no queue, no craziness about anything. So let me write this down, and then we'll just. But is the logic clear? Right? So that's the Bellman-Ford algorithm. It's just for n minus 1 times. Apply relax UV over all edges UV. Note that this is directed, so UV and VU could be different, right? So this step over here, this you can do in O of M, and so overall it's O of Mn. And that is the Bellman-Ford procedure. Works for negative weights. This is really important. Right? Dijkstra does not work when the weights are negative. Right? So if you have negative weights, then this can happen. Clear? And the logic makes sense? Essentially, when you're doing this n minus 1 times, for any shortest path, you're going to end up running in that order. And then doing a bunch of extra relax operations, which are always safe. Okay? So that's Bellman-Ford. Now, Bellman-Ford, with a little bit of care, it's almost. It also can find a negative weight cycle. It can also find a negative weight cycle. This you have to think about a little bit carefully. But essentially, what happens is, suppose there's some negative weight cycle. Then at some point, it's going to do a relax operation on each of these in order. Right? And so somehow it's sort of going to detect that fact. You have to be a little bit careful because there's So the other sort of surprising thing here is that, okay, so maybe I should say something here, like the zeroth step is initialize dist s equals 0, and then for all v not equal to s, dist v is equal to infinity, right? So this is the only place where the source enters the whole algorithm. Because the rest of it, the source doesn't even matter. It's just the initialization where the distance to the source is 0 and everything else is infinity. After that, you're just doing all these relaxed operations and the information gets propagated. Which is, again, like BFS, think of this as like inserting into the queue. Like the first thing that you visit is S and you put it into the queue, and then after that it's a sequence of relaxed operations. So Bellman-Ford can also find negative weight cycles. You have to think a little bit about how to do that. But again, the logic is exactly this. That at some point, relax operations are done in the cycle order. Okay, yeah?
I thought relax only updates the S array.
It updates the est in the predecessor.
Yeah, so then how do the dist values get updated in Bellman-Ford?
I'm sorry, not dist. My apologies. It's not dist. It's, sorry, estimate. Sorry. Yeah, sorry about that. The estimate. Because the dist is the true value. Yeah, you're right. Right, so the estimates are set, initialized, and then it just does this. Yeah?
The negative weight cycle means that there's at least one negative.
No, negative weight cycle means it's a cycle. Actually, let me draw this out again. It means that the total weight on the cycle is negative. And if the total weight on the site is negative, then actually shortest path distances don't exist. Because you could keep taking that path over and over again and the distance would keep decreasing. So an interesting application of negative weight cycles is actually computing arbitrage in financial markets. So what does arbitrage mean? Arbitrage basically happens when you take $1, convert it to pounds. Okay? So maybe you'll get, 80 cents or something. Convert it to euros, then convert it to pesos, convert it back to dollars, and if you end up with actually more than $1, you could just keep repeating this operation over and over again and make money, right? So this happens with any kind of trade. Like if you have any set of trades where you have one currency or one, let's say, one object that goes into another one, you keep doing this over and over again until the number of objects increases, and then you can start doing this. And do you think hedge funds and all these compute these? Sure they do, right? So if they find arbitrage, they will keep. What happens then? What happens then is that when those transactions get detected, everybody else tries to do it, so then the prices will go up, and then it will stop it. Right? And that's why people do high-frequency trading, because if you can do it really quickly, then you can do it in that small time frame when people haven't figured it out, make some money over there, right? You can even get arbitrage if the prices of a stock in Chicago and New York are different, then you try to use that. And remarkably, people were doing that because the New York Stock Exchange is the first place to get the data, but then to send that data to Chicago, it takes the speed of light, right? Because it has to go on a cable. And so people are actually saying that if you put a direct cable, you get the information a little bit quicker, so you could basically trade a little more. And that's how a lot of high-frequency trading started. But a lot of that is related, not all of it, but a lot of arbitrage questions can be converted to finding negative weight cycles if you set up the right network. Okay? So yeah. Okay, so this is Bellman-Ford. It's quite simple. To find the negative weight cycle, yes? Yeah.
Then how do you know that your relaxed operations are done in a cycle?
Okay, so the thing is you're doing relax operations n minus 1 times for all edges. So you're obviously going to do this edge in the first outer loop. Then you'll do this edge in the second outer loop, and this edge in the third loop. You're eventually going to do them. You might do them, so the point is, you might do them out of order, but you'll also do them in order. So imagine, maybe the way to think about this is, so here's your graph. I did relax on everything. So obviously I've done relax on this. Then I do relax on everything again. So obviously I'll end up doing relax on this after I do relax on that. So on and so forth. So I will do it in that order, even though I do more operations. So I'll just draw one more picture to make this clear. So this is, let's just say, all relax operations. All relax operations in one pass over the graph. Then you do it again. You do it again. You do this. You do this n minus 1 times. Which means that if you look at this edge, I'm going to call this E1, E2, E3, E4, E5, E6. E1 is going to be here somewhere, and E2 is here somewhere, E3 is here somewhere, so on and so forth. So once you do all of these, you will do them in that order. That's the logic. Okay? Yeah?
Even you do like relax the every edge in this cycle, then how do you know they actually form a cycle?
Form a negative weight cycle?
Yeah.
I was going to put that in the homework, but so that's going to end up being one of the homework problems. But essentially, it's just this logic. Like you basically use this idea. You have to track a few more things, and you can compute negative weight cycles. You can find them, and then you can also just you can output the negative weight cycle. Okay. All right. Any questions about that? Okay, good. So we're about halfway through, so let's take a short break for a few minutes, and then when we come back, I'll do Dijkstra. Okay, so let's continue. So we just talked about this simple Bellman-Ford algorithm. So Bellman-Ford runs in O of mn time, so it's quadratic time, and it works when there are negative weights. And I said it can also find a negative weight cycle. So I'll give you a hint as to how to do it. You take your graph, you put a dummy vertex, you put a new vertex that just connects to everybody with weight 0. Okay? So you have a dummy vertex that connects to everyone with weight 0, and now you initialize from that source. So that's your source now. This new dummy vertex is the source. Just run Bellman-Ford, and if you think about it, you'll see that essentially you'll be able to detect negative weight cycles. Moreover, not only can you find the existence of one, you can find a negative weight cycle if it exists. Like you can find the specific cycle. Okay? All right. So, just to write this out, clearly Bellman-Ford does O of mn relax operations, finds, SSSP in graphs with negative weights, and can also find negative weight cycles. Okay? And you might ask, can you do any better than that? And for the longest time, no one knew until this is by Feynman in 2024, I think, when the paper actually got published. And he got an improvement. He got like m to the 8/9. Okay, for this problem, and this is like it's like a 50-page paper. Okay, so it's not, it's significant effort. Whereas Bellman-Ford, the entire proof is about a page. Yeah.
Are there real-world applications of Bellman-Ford where 1/9 of the difference makes it?
So it's likely that this constant is not going to be great. So probably not. The other thing about Bellman-Ford is, so what happens a lot when you apply graph algorithms in the real world is it not just running time, but sometimes cache locality matters. So the idea is that you're making these passes over the graph, and usually that's cache optimized. So if you kind of store all these values, these est values and predecessor values in an array, you can just make multiple passes and it'll be much quicker. So this is, at this stage, only of theoretical interest. But typically what one sees is that there's a theoretical improvement that happens, and then 20 years down the line, people figure out how to get the right implementations up. So that's probably what's going to happen. Yeah. So that's what you have when you have negative weights. But there's the famous algorithm of Dijkstra. So, sorry, I think I'm Dij. Dijkstra's algorithm, which you get O of m log n relax operations, and actually technically you can actually make it O of m plus n log n. And this basically finds or solves SSSP with non-negative weights. So the point is, when you go from negative to non-negative, you get a huge improvement. And that's because you can essentially do this sort of crawling argument. So the whole problem in Bellman-Ford is because you don't know what the right sequence of relax operations is. So you just sort of brute force and just do it over all the edges. But if you have non-negative weights and you maintain a data structure, you can be a little clever and you can figure out what is the next right thing to do, right? And that's essentially, that's exactly what Dijkstra does, right? It maintains a priority queue, and the priority queue tells it what is the next correct operation to do. Make sense? And so that is m log n. Dijkstra's algorithm fails when there are negative weights. This is really important. Construct an example. It's not that difficult. You can construct an example with just a few vertices where Dijkstra is going to fail. Okay? Any questions? Should I do Dijkstra? Yes? No? I mean, most of you have probably seen it. I'm guessing you've already seen Dijkstra's algorithm before. Yeah?
I forget why it's unlogged.
Okay, so which means you're asking, okay, you want me to show it. Because it's using a priority queue to do these operations. It's basically going to use a queue, and every time it's going to do it's going to keep inserting into the queue for every time it sees an edge, and that's why it's the m log n. Okay? Yeah.
More of a historical question, but did he write the algorithm knowing it would fill at negative weights?
Sorry?
Did he write the algorithm?
Sure. Yeah.
Knowing it would fill at
Yes.
negative weights?
Yeah. I mean, he was smart enough to know that. But the thing is that in most applications, weights are not negative. Like, think about distances. Like, often, like, I'm actually working with people in like AWS networking, and they use Dijkstra all the time because what you have is an edge has a link has latency, and then you're trying to find the lowest latency path. But latencies are always positive, right? So there you'd have like some mesh of maybe a few thousand routers. Each link has some latency measured, maybe in microseconds or maybe less or whatever, and then you have to build a routing table to decide how to send the packet. And what they will do is they will use those latencies to compute a shortest path, right? So this sort of application of Dijkstra is very common. Yeah.
The latency should be like that, dynamically changing. Do they have to?
Well, okay, it depends. Like, again, you're right, but it could be that maybe the latency is at that point just a function of like the length of the cable. Like then in that case, it's only depending on the cable and not on the machine itself, then it's something static. But if there is something that depends on actually what's going on in the machine, then yes, that does affect these things. And then the routing table has to update. Yeah, you're right. It can be dynamic, but in many of the situations, it's static if the length of the cable, if you're just looking at like what is the latency induced by the cable itself, which is usually like some speed of light or something like that. Yeah. It probably, so in general, it's unlikely that it's going to work because this result just came out. I mean, like, otherwise, this guy wouldn't have had to do all the work. But what you're saying is, suppose the weights, negative weights are bounded. Like, let's say I know that the negative weight is going to be at most like -5. Then I can probably do something where I take some constant factor hit of like a factor of 5. But all of these algorithms are independent of the actual weights. Right? So a lot of those things might start failing if the weights are not integers. Like, what if the weights are fractions, like these latency type settings? There are tricks that you can do to try to mitigate. Suppose you say there's only one negative edge. Then you might say, okay, remove the negative edge, go ahead and run Dijkstra, then put this thing back in and see, and then run Dijkstra again using this, see what, If there are a few negative edges, you can probably make things work. Does that make sense? It's actually a good homework question. Okay. Be wary. Like, you ask questions like, oh my God, then this ends up in the homework. But, okay. Okay, so I'm just going to like really quickly just write out Dijkstra, just so that you have it. I'm assuming most of you are familiar with it. Excuse me. So just very quickly, what is the logic of Dijkstra? Sort of a recap. So it's actually pretty much like Prim's MST algorithm. So the idea is that we have a shortest path tree from the source S to some vertices S, meaning that there's some set, I'm going to call this capital S, so that we have the actual shortest path tree here. Okay? And so the idea is that here S of V is equal to dist of V. Suppose you know this. And the base case for this is, of course, when S is just a single node. Right? When the whole set is just one node, then that is true. And so the question now is, what is the next relax operation to do? Now, in some sense, the obvious thing is you basically look at the edges that are crossing. Right? So I'm just going to sort of make this. So here was S, this is S complement, and then there are a bunch of edges that are crossing over to the edges in S complement. And the natural thing to do is to do relax on one of these edges. Right? So if you remember what Prim's algorithm did to build MSTs, it just picked the minimum weight amongst all of these and said, that's the next edge to take. Why doesn't that work for shortest paths? Yeah?
Because it might be another, like reaching the node to get to that edge might be longer than another path.
Exactly. So you could have maybe this edge is the least weight, but to start from here and to get there takes a long path. Whereas this edge over here, maybe its weight is more, but getting here is really quick, or is getting here is short. So the natural quantity seems to be, if you look at this edge UV, you look at S of U plus the weight of UV, where U is in S, V is in, S bar is like S complement, like the rest of the world. Right? And you minimize over all UV of this quantity. So you're saying, look at your current paths, which you know are correct, add one more edge, and look at the best choices amongst all of those. Then this has to be a shortest path, because if you had to try to go out any other way, it's going to be more than this. And because the weights are non-negative, to go from somewhere and come is going to cost you even more. When weights are negative, that fails. It could be the case that it makes sense to take a longer path initially and then take a bunch of negative weights to cut things back down. Right? Does that make sense? So this is really important. This is why Dijkstra fails. This is why negative weights really make things complicated, because you cannot be like, you don't have this greedy approach where you can basically look at the next thing. Negative weights really complicate things. With non-negative weights, you can just do this minimization. Right? And then so once you find this, then basically what you're doing is you're just doing relax on this edge UV. That make sense? So this is the logic. So I'll just say this again. Say that any shortest path to V going, or I should say any path going to V via some other edge U prime V prime. So this is like U prime V prime. Will have a total weight at least S to u plus that. Right? So S to u plus wv is the shortest path distance to v. Because any other path is going to have at least as much. And this is the logic. Right? And so the whole point is, how do you maintain this? And the moment you see finding min of some set, you should think priority queues. And so you basically store everything in a priority queue, and that's where you get the log n factor from. Okay? So I'll just quickly write down the sort of the code for this. Dijkstra's algorithm, and you'll see that like BFS, Prim, Dijkstra's algorithm are in some sense very similar to each other. It's the same logic, except here you have a priority queue and not. So you initialize your set to be. I guess you initialize this to be the null set. You set estimate S is equal to 0, and estimate V is equal to infinity for all V not equal to S. Then you create a min heap Q over all vertices where est V is the key. Right? So you're creating this min heap, and your estimate is your key. And note that over here, what we'll basically do is we'll do a relax operation on this. That'll update the estimate, and we use the estimate. And so we'll just do while the queue is non-empty. You do an extract min from the queue, call it V, add V to the set of things that we've already visited, and then for every, I'll say X in the out neighborhood of V. So this is the out neighborhood, everything in the out neighborhood, we will just call relax Vx. And if relax Vx reduced the estimate for X, then update, or I would technically decrease the priority for X in the queue. Because this is the entire algorithm. Okay, does this make sense? So you basically call the relax operation. So this is just saying that what we'll end up doing is for all of these edges, we're going to call the relax operation. And so suppose the relax operation changes this estimate, then you have to update the priority. Right? So you have to do this like decrease priority in a min heap. Okay? And then when you do the extract min, you're always getting the one that minimizes this quantity, the estimate plus the weight. Okay? And so the extract min, this is going to cost an O log n, and this operation is also going to cost O log n, and so it's a total of O of m log n, because we're effectively doing this potentially for all edges. Every time you visit a vertex, you're looking at all the neighbors. So O of n log n time. And again, if you use something called a Fibonacci heap, you can get O of m log n. There's a way of doing this. There's a funky data structure that actually gives you what's called amortized constant update. So it's a really complicated data structure. No one really uses it in practice. But theoretically, you can actually get O of n plus n log n. You can make this constant time, but this extract min is still going to be n. Okay, which is not that important, but the point is you get this O of m log n. Okay? Yes?
One for when you initialize the would you include the source node?
So actually, you don't have to, because the way I've done this, the very first extraction is just going to extract S, and it's going to add it to the set.
Okay, and then second question, inside the queue, that'll be all the vertices that are part of the S set, right? Like every edge in Q will be in the S and not the S.
No, so technically what's in the queue are everything in S and their neighbors.
And their neighbors.
The neighbors are also going to be in the queue, because the neighbors will all have a non-infinite estimate, and they're going to end up in the queue. Let me be precise. Technically, everybody's in the queue.
Sure.
Everybody's in the queue with infinite estimates. But the ones that are going to have finite estimates are the things in S where it's converged, where you know you have and the neighbors where you're still not sure. But those are the ones, because those are all the edges that you've already processed.
And then you're keeping vertices in the queue, not edges.
I'm keeping vertices in the queue, exactly. And yeah, so that means the size of the queue is small, but the number of operations is large, because I'm doing potentially, so think of it this way, that for this vertex here, there are all these edges that are coming in. So this is S and this is S. For each of these edges, I'm going to apply a relax operation, and maybe this relax operation reduces the estimate, so I have to update. Then this one also reduces it further, so I have to update. So all of these edges could end up updating the estimate. Even though it's only one of them that's important, you don't know which one it is, so the algorithm is just going to do them in some order. And that's why it's going to cost that many operations. In practice, probably like as soon as you hit the first one, maybe that's good enough, and then that saves the time. Which is why in practice, the Fibonacci heap isn't really going to change things as much. The issue, why do people do Dijkstra with A star? They do A star not because they want to get the log n down, because the m is too much. You don't want to explore the entire graph. So you kind of say there are some portions of the graph you're just going to ignore because you don't think that like there's some very expensive edge, it's just not worth taking at all. And often when you're doing A star, you're only looking at getting to one destination, not all. That's the other change, which is like the by BFS, right? If you only care about one destination, then you can beat BFS. But if you want to reach all destinations, you have to spend linear time just to look at everything. Yeah? Any questions? Okay, so I'll just, what is it that I expect you to know? Well, I expect you to know Bellman-Ford and Dijkstra. Those procedures, right? That you should know. And you should understand this notion of negative weight cycles, the fact that Dijkstra fails when there are negative weights, construct an example, figure out how to find negative weight cycles using Bellman-Ford. And as explained, the idea is not very difficult. You just start with a dummy source. Okay? And understand this notion of relax operations. At this stage, given that you've seen Dijkstra probably once, maybe twice in your life, I think at this point it should be I promise you it'll be quite clear what's going on. Okay? All right. So, the next thing to talk about in the context of shortest paths is a problem called APSP, which is all pairs shortest paths. So what I want to output, something called the distance matrix. So I just want to output dist of uv for all u and v, for all the vertices. So if you think about it, your output is like n squared. So in this setting, for all pair shortest path, typically the input is the adjacency matrix. Because the output is, usually you think of the input being an adjacency list because you don't want to store like this. You don't want to store all these zeros. But in this case, because for all pair shortest path, the output itself is so large that we'll see what the input is an adjacency matrix, we can actually get some better algorithms. Okay? So what is the obvious algorithm? What is the obvious algorithm for all pair shortest paths? We've just done single source shortest paths. So what should you do? Yeah? Just run it from every source, right? Run your favorite single source shortest path algorithm from all vertices. And so what will you get? You just run SSSP from all vertices. So for general weights, that's going to be n Bellman-Fords. Or maybe you could use Feynman's algorithm, but essentially what you're looking at is mn squared, or maybe it's like, whatever, 16 over 9, so it's some m times this thing. And if it's non-negative, then it's n Dijkstras, and we're looking at something like, I'll just say mn log n. Or you could even think of it's like, I should say it's, sorry, m squared log n. Wait, no. I'm right. mn log n. Right? M log n for each Dijkstra, and you did n of them. So mn log n. Great. And so, what I'll give you is a dynamic programming approach called Floyd-Warshall, which uses some ideas from matrix multiplication. It's related to matrix multiplication in some ways, but it's basically just n cube. Okay, so Floyd-Warshall will do it in n cube time. And so the thing to note here is that if m is like linear, if m is like n, then you might as well just do n Dijkstras. But m could be as large as n squared. Right? If you're looking at a dense graph, that's what's called a dense graph. Like most pairs are connected. So especially in a lot of like router type settings where you want to connect everything to everything or many things to get sort of get a lot of redundancy, you could have m being quite large, in which case both of these, the general weights case, it's going to be n to the fourth, and this is n cubed. And this would be n cubed log n, and you can save a log n, yeah?
And so why does Dijkstra have the same running time for all pair shortest paths as it does for just the normal?
So normal is m log n. This is mn log n.
Oh,
There's an extra n factor there. Okay? Okay, so Floyd-Warshall is going to run in n cubed time. I don't have enough time to finish Floyd-Warshall today, but actually it's just like 15 minutes. So I'll give you the basics, and probably in the next lecture we'll just finish it off. It's also a very nice application of dynamic programming. So it's another useful thing to look at. So let's start with a basic recurrence for shortest path distances. So this is where we have to think of some table or some recursive procedure. I'm going to write it using a subscript because it's going to be a little more convenient. So I'm going to say dist underscore k of uv. This is my function. This is the shortest path distance from U to V using at most k edges. So one way to think of it is like dist k of uv, if the number of edges you need is a lot, it's just going to be infinite. But what we'll see is that if we build these sorts of tables, we can just use the previous tables to do an update quickly, and then we can just compute all pair shortest path in one go. Okay. So what is dist 1 of uv? This is just going to be whatever the weight is. So it says that if you can only take one edge, then you're just going to take whatever the weight is. And if there's no edge, we'll say the weight is infinite. Right? So if uv is not an edge, then set the weight is infinite. Or you can just put this in the adjacency matrix. So the adjacency matrix, you can think of when there's no edge, you just say infinite weight, infinite. Okay, so how would you do this? What is the recurrence you should write here? You want to write dk in terms of, I should say dk uv. You want to do dk in terms of dk minus 1. How? So that means you want to go from u to v. And you want to see what is the shortest path that uses k edges. Clearly, there is a shortest path that uses k minus 1 edges. That's the, right? Which you've already computed. So what is the recurrence I should write here? Some min over something. Yeah? So it's dk minus 1 plus what? Plus whatever that weight is, right? And so you minimize that over all the neighbors. And so in this case, we're thinking adjacency matrix, so like everybody's a neighbor. Just put infinite weight if you're not a neighbor. So it's the minimum over all vertices in the set of dk minus 1 going from u to x plus the weight of x to v. Right? Does this recurrence make sense? Right? So what you have is, and the true distances, and assuming no negative weight cycles, the true distances are just going to be dn minus 1 of uv. Because when it's n minus 1, it means that I've taken a path of length n minus 1. And I'm never, because there are no negative weight cycles, I never intersect with myself. The path never intersects, so it's n minus 1 edges. Yeah?
Would it be equivalent if instead of min over all edges, for all vertices, for all the outgoing neighbors of u?
All the in neighbors of v. Yeah, either way, you could do it from source or destination. Yeah, you could do that as well.
Okay, so what is that theoretically?
That would save you some, but we're thinking of an adjacency matrix representation. So it really doesn't, and the picture that you should have in mind is that you're in this like M being almost n squared, so like a dense graph. So maybe vertices are connected to like half the other vertices. So in which case that savings will give you like a constant factor, but in terms of the asymptotics, it's going to be easier to define the dynamic programming this way. But you're right, absolutely. Okay? All right. So once you have this, you could set up your table. Right? So I'll say the dp table, I'm kind of just write it like this. It's going to be u, v, k, like the three things here. Right? And I say t of u, v, k is I just apply the same logic there. So the min of x over all vertices of d of u x k minus 1 plus the weight of x to v. So this gives me the way to update my table. And so the table has basically theta of n cube entries, right? It has one for U, one for V, and one N for K. And each entry takes theta of N time to update. So you get basically, I'll say, theta of N fourth algorithm. Right? So this is like your basic, simplest dynamic programming formulation. It's no better than doing anything else, but it's actually really simple. The nice thing is that this is a really simple procedure now. And you get all pair shortest paths. What's kind of remarkable in this is like, I think one of the problems is we often teach Dijkstra as the first algorithm. And so you start thinking of heaps and traversals and all of that. But actually there are much simpler algorithms that compute shortest paths, just using like Bellman-Ford or this procedure. Here you don't even have a relax operation, right? You're just doing this over and over again. You're just doing this dynamic programming update. So you start with k is equal to 1. You know how to update that. You know how to initialize that. You put k is equal to 2. Then k is equal to 3, k is equal to 4, so on and so forth. Okay? Make sense? Okay. So what Floyd-Warshall does is basically says, how do you improve on this idea? So first what I'm going to show is there's a simpler idea that gets almost all the improvement, and then Floyd-Warshall makes it even better. And so the simple one is something that I'll write down here. I'm just going to change this recurrence and say, instead of that, I can also say this. It's the min of dk over 2 of ux plus d of k over 2 xv. Instead of trying to go all the way to the end, figure out what the midpoint is. Okay? And just imagine that k is a power of 2. Imagine k is a power of 2. It's not that critical, but just it's easy to think that way. So it's saying that instead of the dynamic program trying to go all the way to the end and then figure out the next edge, it's just figuring out the midpoints. And if all the midpoints have been figured out, then you can get the next. So what this means is that in every iteration of the dynamic program, so in every sort of, what happened in every iteration here is you increase your knowledge by 1 hop. And with this, you'll actually double the number of hops in each go. So what you can do is you can actually get a dynamic programming table where instead of n cube entries, there are only n squared log n entries. And it's going to be much smaller. So the table is much smaller, and then the updates are going to be quicker. So that's the logic. And then Floyd-Warshall does something even more clever on top of that. So I think I'll end here. Next lecture, I'll come